Well, what we're going to do is, this is non-spontaneous, so what I'm going to do is I'm going to crank up the power on the power supply. I'm going to crank it up to more than 2 volts. If I crank the power supply up to more than 2.2 volts, then this is what's going to happen. I'm going to oxidize my chloride. Electrons are going to be sucked in here, and then I'm going to force them out onto water. I'm going to reduce my water.
Oh, we just see a yellow green gas now?
Yeah, right. And so what we're going to see is we're going to see chlorine gas start to... Yeah, we're going to see chlorine gas start to bubble off this electrode.
Nice.
Chlorine gas. And then at the other electrode, we're going to see hydrogen gas bubble off this electrode. Right. And so we'll get hydrogen gas and chlorine gas. But is hydrogen gas and chlorine gas a stable mixture? No, it's an explosive mixture.
Uh-oh.
And so I need to build a little barrier here to prevent the hydrogen gas from coming into contact with the chlorine gas. Otherwise, I'm going to be in trouble. I'll have an explosion. And so you build a little wall here so the hydrogen gas can go off on the left and the chlorine gas can go off on the right, and we can make highly reactive chemicals. And so there are three reasons we do electrolysis. 1, to recharge secondary batteries. 2, to make highly reactive chemicals like hydrogen and chlorine. And 3, for electroplating, which we'll talk about next. Well, here's a reactor here. This is producing sodium metal. You know, what if I wanted to produce sodium metal? Then I have to get rid of the water. Because if I look at the reduction potential, the water, you know, sodium's reduction potential is very low. And so if I get rid of the water, if there's no water around, then the highest reduction potential will be sodium. Well, how did I get rid of the water? How you get rid of the water is you don't do this. You don't do electrolysis of aqueous sodium chloride. You do electrolysis of liquid, pure sodium chloride. That is molten sodium chloride salt. If you electrolyze molten sodium chloride salt, you get rid of this bottom row, and that's the redox that's going to happen. In fact, what you're going to get is you're going to get chlorine at this electrode, and you're going to get sodium metal at the other electrode. It turns out sodium metal is less dense than molten sodium chloride, so the sodium metal will float to the surface, and chlorine will be a gas. It will be molten, because the sodium metal will be melted because it's hot. And so we just have a barrier here. And so rather than generating hydrogen here, we have sodium metal if we get rid of the water. And so this is another way we could generate sodium metal here. In mercury, chlorine goes out, chlorophylline. Electroplating is, you just put like copper. If we put copper 2 ions in here, and copper 2 has the highest reduction potential, then those will be reduced. So you can plate out one of the electrodes. We can plate out this electrode over here, which is the cathode. At the anode is always where oxidation occurs. So which one of these is the anode, which one is the cathode? Which one is the anode, which one is the cathode? The left is where reduction occurs, the right is where oxidation occurs. For electrolytic cells, we write it this way. Electrolytic cells we write backwards because we want the electrons to flow right to left. And so here, this would be the anode. This is the anode of the electrolytic cell. This is the cathode of the power supply.
You know, for anybody confused on that, they were talking about just the easy way to remember where oxidation occurs. The O and the A are both vowels, and then the cathode and the R are both consonants.
Oh, okay. Another pattern.
Yeah.
OA. OA.
Yeah.
Both valves.
And then CR on the other side.
CR, both
CR.
constant.
Cathode reduction.
Good. Thanks.
You're welcome. Bonus point.
Yeah. Thank you.
You're welcome.
They don't show a good example of electroplating, so. Oh, metal refining is another one. All right, actually, that wasn't the last topic. The last topic is cell stoichiometry. Cell stoichiometry is this. We can use Faraday's as a conversion factor. So, for example, we can figure out how many moles of reaction we have by looking at the moles of electrons transferred. We can actually measure the moles of electrons transferred by using an ammeter. An ammeter versus a voltmeter. A voltmeter measures the pressure, the force on the electrons. An ammeter measures how much charge passes through. And an ammeter is going to measure it in amps. And so if we measure the number of amps that passes through an electric wire, we can figure out how many moles of electrons just pass through. And using half reactions like this, we can do some stoichiometry, because the stoichiometry is we have 2 moles of electrons for every 2 moles of water, and 1 mole of hydrogen and 2 moles of hydroxide. Over here we have 2 moles of electrons for every 2 moles of chloride or every 1 mole of chlorine. And so we can just do stoichiometry just like we did in Chem 1A. If we can calculate the number of moles of electrons, and we can calculate the number of moles of electrons just by using the definition of an amp and measuring the amp. And so 1 amp is defined as 1 coulomb per second of charge. And so we'll need to know how long. So for example, if we have 60 seconds at 10 microamps, then we could figure out how many moles of electrons just transferred. And so this would be 60 seconds, 10 micro would be 10 times 10 to the minus 6 amps, which would be coulomb per second. And so that tells us how many coulombs, and then we just use Faraday's, 96,485 coulombs to convert it into moles. And so now we have the number of moles of electrons, and so we can figure out how many grams of chloride I just consumed, or how many grams of hydrogen gas I just generated, etc. And do stoichiometry that way. That's actually the last section of chapter 20. So we'll stop here, we'll take a break, and then we're going to look at, it's going to be a very short lab, but can you check out a model kit during the break?
The ball and stick models?
Yeah, the ball and stick models. I got to let them know that we're doing that.
Sandra. Kelly.
I was